in application of derivatives, in first two lectures you have seen the very important concept of geometrical meaning of derivative, and we have also seen how we can find the equation of tangents and normals. Now the second most important application of derivative, which is required for the study of physics, is the concept of maxima and minima of a function. And in this regard, you have seen just an introductory lecture on this maxima and minima previously. Actually, in that lecture, I have discussed in detail the importance of the concept of maxima and minima for a physicist. When you study physics, you need the concept of maxima and minima, and where this concept is needed, I have discussed in very detail in the previous lecture. Now from today we will see actually the mathematics of this maxima and minima. Okay, that is, we will discuss the concept of maxima and minima in very detail by taking important illustrative examples. You will see that in this series of lecture on maxima and minima, we will solve so many important problems which have been actually asked in different standard competitive examinations like IIT JAM, okay, and NET and JRF examination. So this series of lecture will be very useful for you if you are a student of physics or if you are a student of mathematics. Actually, this will be very helpful and very interesting for you. Okay. So this is the first lecture on the concept of maxima and minima after the introduction. So in this lecture we are going to see two very important and very simple concepts. The first concept which we will discuss is which is called actually first fundamental theorem, or you can say this is just definition of maxima and minima. And another very important concept will be of critical points. Actually, for dealing the concept of maxima and minima, it is essential to know the idea of critical points. So before knowing in analytical way the condition for maxima and minima of a function, definitely you should know about critical points. So one by one we will learn about the definition, or you can say the first fundamental theorem, or the condition for local maxima. Okay, and after that we will see the concept of critical points. So how this local maximum value of a function will be defined, and what will be the local maximum value of a function. When you say local maximum, actually we define two maximum value of a function. First one is called local maximum, and the another is called global maximum. Global maximum. But here I am just talking about the local maximum value of a function. When you say local, it means you have to compare the value of a function at a particular point with its values at close neighboring points of that very point. It means the value of a function may be maximum at a particular point in comparison to its value at the close neighboring points, but it may not be an absolute maximum. Somewhere its value may be greater than that. So it is called local maximum. For a practical example, if you see that there are three persons standing at a place, and among those three, let us say those three are A, B and C, and among these let us say this B is the oldest person. It means the age of this B is greater than A and C. So here the age of B will be maximum in comparison or larger in comparison to A and C. Okay, but when we will compare the age of this B with the age of the whole population of this world, can you say that the age of B will be the largest age? No. So global maximum and local maximum are entirely two different things. When we talk about local maximum, we always compare the value of a function with its value at local points or the points in the close neighborhood of the point under interest. So let us see this figure. Actually here I have considered an arbitrary curve. This is an arbitrary curve. You can see this figure, and this curve is represented by an arbitrary equation y equal to f of x, because you know any curve, the equation of any curve is simply a relation between the variables y and x. Okay, so y equal to fx, this is just an arbitrary equation of this curve. Okay, and I have marked a point P here. Okay, and corresponding to this point P, the value of x coordinate or value of x, you can say, is equal to OM. OM is the value of x coordinate corresponding to this point P, which I have marked by A. It means you have considered that OM is equal to A. Now we consider two close points P dashed and P double dashed, which is very close to P, although in figure these points are far separated from P, but mentally you have to think that this point P dashed and this point P double dashed are very close to point P, and corresponding to the point P, the value of this function y equal to f of x, you can see, is f of A, and this is let us say equal to OA. It means OA is equal to f of A. You can see this figure. Now corresponding to this close points point P dashed, which is close to P, the x coordinate is what? This is OM prime, and I have considered this A plus H. It means the x coordinate of this point P dashed is greater than A by H, and the another close point P double dashed, for this the x coordinate is OM double dashed, and this is, let us say, A minus H. Actually here this H is a very small number. It means A plus H and A minus H are very close to A. So I have told you that these 2 points P dashed and P double dashed are very close to point P. Now you can see that the value of this function corresponding to this P double dashed and P dashed will be what? This will be f of A plus H and f of A minus H. These are the value of the functions f corresponding to x equal to A plus H and x equal to A minus H. If you consider that this H is very small, this is very small, okay, very small, then you can see that this f of A is greater than f of A plus H and f of A minus H. And if f of A will be greater than f of A plus H, it means f of A is greater than f of A plus H. Okay, and this f of a is also greater than f of a minus h. Okay, it means where actually this a belongs to, you can say, a minus h comma a plus h. It means the value of a lies between these in this closed interval. In fact, in this condition, when f of a is greater than f of a plus h and f of a is greater than f of a minus h, then we simply say that this function f of x has its maximum value, or it has a local maximum value at this point P or at x equal to a. And this f of a will be called its what? Local maximum value. F of a is its local maximum value. I think you have clearly understand what I have actually told. Okay. So now for your convenience, I have actually written all these facts which I have just explained. I have written each and every point for your convenience so that you can note down these facts in your notebook, and that will be very helpful to you. Okay, so now let us see. I have just mentioned all those facts which you have seen just now. I have mentioned that a function f y equal to fx is said to have a local maximum. Mark it, local maximum, not global maximum. Or this local maximum is also called relative maximum. Why it is called relative? Because we compare the value of the function with its values at neighboring points. Okay, so it is also called a relative maximum. And this function y equal to fx will have a local maximum or a relative maximum value at x equal to a when this a belongs to a minus h and a plus h. In fact, in that condition, if f of a is greater than f of a plus h and f of a is greater than f of a minus h, where h is very small positive arbitrary number. Actually, in that condition, you say that this function y barabar fx has a local maximum at this point x equal to a. And the value of fx corresponding to x equal to a, which is f of a, that is called local maximum value of the function fx. It is its local maximum value. I think you have definitely understand this. Now, in the similar manner, you can understand what is local minimum value of a function. Local minimum value. And for this, you can see this figure. Again, I have considered an arbitrary curve defined by the equation y equal to fx. Okay. And I have actually considered 3 points. You can see I have considered a point Q corresponding to which the x coordinate is equal to ON, and this ON you can see is equal to A. Okay, ON equal to A. And corresponding to this point, the value of the function is f of A. F of A. Okay. Now again, we consider 2 closed points. First one is Q dashed and another is Q double dashed on the same curve. These 2 points Q dashed and Q double dashed are very close to Q. As close as you can imagine. Okay. And corresponding to Q dashed, the value of x coordinate is A plus H, and that corresponding to Q double dashed, its value is ON double dashed, which is A minus H. Now, you can say that this function y equal to f of x will have a minimum value at x equal to a, where a again belongs to the interval a minus h comma a plus h. Okay. So f of a will be called its minimum value in comparison to the values at the neighboring point, when actually this f of a, this will be less than f of a plus h. It means when x is a plus h, then its value is f of a plus h, and this f of a is smaller than f of a plus h. And this f of a is also less than f of a minus h. It means if the value of a function at a particular point x equal to a is smaller than its values at the neighboring points, then we say that the function f of x has a local minimum value at the point x equal to a. Okay, and this fa will be called its local minimum value. And again, actually I have mentioned all these facts for your convenience, and so you can write down these facts in your notebook. So let us see, I have mentioned it here. A function y equal to f of x is said to have a local minimum or relative minimum value at x equal to a belonging to the interval a minus h and a plus h if f of a is less than f of a plus h, f of a is less than f of a minus h. Only then you can say that this fx has a local minimum value at the point x equal to a. Here this a h is a very small positive number, you know. So I have mentioned that h provided us is sufficiently small. Okay, and this f of a will be called local minimum value of this function. Okay. Actually, till now you have considered the function y equal to f of x, and let us see the figure. Observing the graphical plot of this function y equal to fx here in this figure, and also in this figure, you can say that we have considered actually the continuous curve. We have considered continuous curve. But this concept of local maximum or local minimum is only for the continuous curve? Answer is no. Actually, when our curve is either continuous or discontinuous, the function is either differentiable or not differentiable. Actually, all in these situations we can define the local minimum and local maximum value of a function. Okay. Actually, I have mentioned this fact here in the remarkable fact that first fundamental theorem is applicable to all functions which will be either continuous or discontinuous. That function may be differentiable or non-differentiable at x equal to a. Because you know that if a function, let us say f of x is discontinuous, it is not a continuous function, discontinuous at x equal to a, then you know that the derivative of any function at its point of discontinuity, that x equal to a, is undefined. This is a very important fact of mathematics, that derivative or slope, you can say, of a function f which is discontinuous at point a, that is equal to infinity, that is undefined. It means at the point of discontinuity you can't find the derivative of a function, that is simply undefined. But even at that discontinuous point, we can define the local maxima or minima. You can see this figure. Actually here in first figure, this is the graphical plot. There is a function, let us say f of x, and this curve represent this function up to this point, let us say P. But and corresponding to P, x is equal to a. But at x equal to a, the value of the function abruptly falls to this point, and then the graphical plot is like this. So if you want to define the derivative of this function at this point P and this point Q, you can say that there will be two slopes. Actually, slope for this second part of the curve will be different, and that for this first part of curve will be different. So we simply say that at this point of discontinuity, we cannot define the derivative of this function. So this is a discontinuous function. But here, first of all, this function has the value corresponding to point P, and after that it discontinuously fall to this point Q. So this point P, the value of this function f of x corresponding to point P will correspond to a local maximum value. On the other hand, if you consider that this is our function, this function actually has, let us say this function is varying like this, and it reaches to again to this point P and abruptly rises to this point Q. Then this function will be discontinuous at x equal to a, and this point P corresponds to its minimum value. So in these two figures, I have shown actually two discontinuous functions, graphical plot of discontinuous functions, and at this point of discontinuity, the function may have a local maximum or a local minimum. Although the functions are not continuous, they are not differentiable at the point of discontinuity, because I have told you that at the point of discontinuity, the slope of the curve is undefined. Okay, slope of the curve will be undefined. Now, another remarkable fact you can see here, that when you say that a function is maximum at x equal to a function a f of x is minimum at x equal to a, actually the point of maxima and minima are collectively called point of extremum. Point of extremum. When you say extremum, that means either maximum or minimum. So the points of minimum and maximum are called extreme points or points of extremum of a given function. Okay, so you can use this term. This term is used in your textbook, so there should be no confusion when you say extremum value of a function. That does not mean only maximum value or only minimum value. Extremum value means either maximum value or minimum value. Both are called extremum value. Okay. So this is the first fundamental theorem regarding the local maximum value of a function. Okay. And we have learned that this local maximum value of a function may be defined for a continuous function, for a differentiable function. It may be also defined for discontinuous function and non-differentiable function. Okay. This fact is very important for your objective question. In your examination, there may be asked that if a function is discontinuous, can you define its maximum value? Can you define its minimum value? If a function is not differentiable, can you define its maximum value or minimum value? Answer will be yes. Maximum value and minimum value of a function can be defined even when the function is not continuous, function is not differentiable. Okay, so I think we have definitely understand all these facts. So now we will see the another important concept of this lecture, which I have told you earlier, that we will see the concept of what? We will see the concept of local maxima, we will see the concept of critical points. Okay, critical points. So now let us see what is the concept of critical points. When you say critical points, actually these are the points defined or lying in the interior of a closed interval. Critical points are defined for the these are points actually corresponding to the interior of a closed interval. Okay, let us say that this is a closed interval a and b. You know that this a and b are the boundary value of this interval, and this boundary value will be never critical point. The value of x which will lie between this a and b, that will be actually the that critical point or a stationary point of a function. So what are actually the condition for the critical points? This critical point is also called a stationary point. Stationary means constant. Actually, there are three important conditions through which you can check that a given point is a critical point of a function or not. Among these 3 points, one of them is very important, but there are 3 conditions to check the existence of critical point. Actually, the points where f of x does not exist, it means f of x will be undefined. That point will be also called a critical point. Okay. The another condition is if you consider that your function is y equal to fx, then the critical points correspond to the points for which derivative of this y with respect to x, or you can say f dash of x, vanishes. It means these are the points where slope of this curve is equal to 0. Okay. So another condition for finding the critical point is what? The another required condition is f dash of x should be equal to 0. And the third condition for finding the critical point is f dash of x does not exist. It means when you will find f dash of x, that will become undefined. So these are the 3 important conditions for finding the critical points of a function. But remember, always we find the critical points if the interval is mentioned, then you have to select the value of x which is in the interior of the interval. This will be actually very clear to you when we will solve a particular example for clarification. And so, to clarify the idea of critical points, how we will actually obtain the critical points for a given function, we will see a very important example. Okay, and as I have told you, although there are 3 conditions to find the critical points of a function. First one says f of x does not exist. Third one says f dash of x does not exist. And the second one is f dash of x is equal to 0. This is actually the most important condition for finding the critical points of a function. In most of the problem, we use this second condition for finding the critical position. If you are given a equation of a function, okay, or equation of not a function, you are given equation of a curve, and you have to find the critical points lying on that curve. Then you have to see that the given equation of the curve is differentiable or not. Differentiable or not. If it is differentiable, first of all you have to find f dash of x. Then you should equate it to 0 and solve the equation. You will get the critical point. But if the function is not differentiable, then we use the third condition. Okay, third condition, if it is not differentiable. But in most of the problems you will see that the given equation of curve will be differentiable. So in 99.9% of the problems, this second condition will be used for finding the critical points on a curve or of a function. Okay. So now let us see an important example to clarify this idea. I am taking a very important example here, and after this example everything you will know about the critical points, and you can solve any problem based on finding the critical points of a function. Okay. So what is this problem? The problem says that find the critical points of the function f of x equal to this much, that is 4x cube minus 6x square minus 24x plus 9. This is actually equation of a curve, you can see. And what are the intervals in which we have to obtain the critical points? It is mentioned in this example, you can see. The first one is you have to find the critical point when x belongs to the interval 0, 3. Another is x belongs to the interval minus 3, 3. And third one is x belongs to the interval minus 1, 2. Okay. Now you can see the given function. The given function is what? This is 4x cube minus 6x square minus 24x plus 9. This is the given function. And you can see that this given function is differentiable. So we will actually use the second condition which we have learnt here. You have to find first of all the derivative of that function, and for getting the value of critical points or for locating the critical points, you should equate this derivative f dash of x equal to 0, since the function is differentiable. So you can see I am just finding the derivative of this function. This is f dash of x, which means df by dx. And you will easily differentiate this. Actually all this differentiation is based on the formula d dx x to the power n, which is nx to the power n minus 1. This is the first elementary formula for differentiation, and you all know about it. Okay. So what will be the dc of this function? This you can see this will be simply 12x square minus 12x minus 24. 9 is a constant, so its dc will be 0. And you can take 12 as a common factor. So f dash of x is equal to 12 times x square minus x minus 2. Okay. Now we know for critical points f dash x equal to 0. And f dash you have obtained, this is equal to this much. So this will be 12 times x square minus x minus 2 equal to 0. But as you know that this 12 is a non-zero number, so you can definitely say since 12 is not 0, so x square minus x minus 2 will be equal to 0. This is just a quadratic equation in x, so definitely x will have two values or two roots. This equation will have two roots and x will have two values. And you can easily find those two values of x by factorizing the equation. You can see this can be written as after breaking into factor x square minus 2x plus x minus 2 equal to 0. Since x minus 2x, that will be simply minus x. Now take this x as a common factor in first two terms. This will be x times x minus 2, and in the next two terms we take 1 as a common factor. So this will be 1x minus 2, and that is equal to 0. Now this will be equal to x plus 1 into x minus 2, and that is equal to 0. And so since the product of these two factors is 0, so each factor can be equated to 0. So you can write x plus 1 equal to 0, and so x is equal to minus 1. And x minus 2 equal to 0, and so x is equal to plus 2. So you can see there are two values of x. First one is minus 1, another is 2. Okay. But in this question, interval has been defined, and in that interval you have to now find the critical point. You have seen that the first interval is x belongs to 0, 3. This is a closed interval. Now see the value of x which we have obtained here. You can see that this minus 1 is less than 0. Okay, less than 0. And also it is less than 3. Less than 3. So this minus 1 is outside of this closed interval. And you have learnt that the critical point are points in the interior of the closed interval, not in the exterior. So this minus 1 will be not the critical point in this for this interval. Okay, minus 1 will be not critical point, although we have obtained that x may be minus 1 and may be plus 2. But for this interval, since minus 1 lies outside of this interval and the exterior point of the interval is not critical point, that must be interior point. Okay, mark it. So in this definition, I have written here that all those points in the interior of an interval, mark this. Okay. Now see the another value of x. Another value is 2, and you can see that actually 0 is less than 2 and this is less than 3. So you can say that this 2 lies in the interior of this given interval 0, 3. So this x equal to 2 is only the critical point. Okay. So answer of this first part of the problem will be what? That will be x equal to 2, which is the critical point of the given function in this interval. I think we have clearly understand what I am telling to you. Okay. Now the another interval in this problem is x belongs to minus 3, 3. Now let us see. This minus 1. This minus 3 is less than minus 1. And this minus 1 is less than 3. Okay. Again, the another value is 2. And you can see minus 3 is less than 2. And this is less than 3. What does it mean? It means both of these two values of x, that is x equal to minus 1 and x equal to 2, both values of x minus 1 and 2 lies in the interior of this interval. Okay, both of these. So these two values of x will be called critical points in this case. So for the second part of the problem, the critical points are both x equal to minus 1 and x equal to 2. Both are the critical points. Okay. Have you understand or not? Definitely you have understand. Okay. Now let us see the third interval given in the problem. The third interval given in the problem is x belongs to minus 1, 2. It means this, you can see our values of x after equating f dash equal to 0 are minus 1 and 2. So this minus 1 is equal to minus 1. This is the lower boundary of this interval, and 2 equal to 2. So these two values of x are the boundary values, not the interior values, but boundary points of this closed interval. But as the definition says, the critical points must be the interior points. So you can say that -1 and -2 lies at the boundary of this interval, not in the interior of this interval. So these 2 points cannot be the critical points. So for this interval there is no critical point of this very function. So I have mentioned it here. You can see that then no critical point. No critical point. Why? As both x equal to -1 and x equal to 2 become the boundary points, but critical points are always interior points of an interval, not boundary points. So for the last interval there will be no critical point. Okay. So I think the idea of this critical points is now definitely very clear to you. It is my keen faith. Okay. Can I believe it or not? I think I am correct that now you know everything about the critical point. And you will see this will be always needed when we will study the condition for maxima and minima in the forthcoming lecture. There you will actually find the use of the concept of this critical point. Okay. So thank you very much.